Hi guys, video number 9 in how to make a chess program in Go. I have done quite a lot of homework. I have done some homework. I did this bitboard. I had this bitboard.go before, but it was more or less empty. Now we have a bitboard.go program. We will look at that later. And we also have this Crosslinks.go with Crosslinks logic for that. I open Crosslinks.go. So first I move this type Crosslinks from position.go to here, where it should be. So we have these 4 constants: short for white, long for white, short for black, and long for black. And they just set different bits, 4 different bits within the Crosslinks variable. I have this method, parse Crosslinks, that sets the Crosslink privileges according to these K and Q and things, uppercase, lowercase, that we find in the fence string. If we take a look in position.go, I have made some changes. You can see I have an init fence square to int. We will look at that later on. I also added this role 50 int to the board structure because we need to take care of that number, the 50 rule move number. Of course we have that in clear as well. I set rule 50 to 0. And in parse fen, now we can actually set pieces on the board because we have a board. And we also can take care of, I put code for taking care of these. Let's open up so we can look. So here we set this white or black to move from the fence string, and further down here we set Crosslinks and use that parse Crosslinks that we looked at before. The EP square we are set to what they say, if there is any, and also the 50 move rule. Now we have this 50 move rule in the board structure. Somewhere here, I don't see it. Here we have it. When we set up the board, if it's a number, we set square to empty that number of times. We loop here about that. If it's not the number, it's a piece, and we need to translate that piece into our internal representation of the pieces. White pawn is 0, black pawn is 1, and so on. So let's take a look on the translations between fence square to internal integer, both ways. So we are using a map to go from fence string to the number. So the fence string A1 go to the A1 that is a constant, that is a number. And we use this map for that. We have a similar map to go the other way around. And here we init that. The other way around, if I have A1 that is 0, sometimes I want to have the string A1. So we have a square to fen table as well. And we set that here. I also added these 2, what you call that, vectors, strings really. If I use the piece without color, for instance, knight, that is 1, I get index 1 there. We also have similar for piece with color. I have this set square, so let's look at that too. Find set square like that. Okay, here is set square, the method under board structure. To set the square on a certain set a piece on a certain square in the board, and we just put it into that square, the right square. The P12 is the piece, it's the piece with color. But if it's empty, we put in an empty square, and if it's an empty square, we clear the bitboard. We will look at the bitboard later. I have done some things with bitboards as well. So clear that bit for white, and we clear that bit for black, and we also clear all the piece types bitboards on that position. If it's a king, we need to keep track of that king. We have this special array with the two kings. We set the bitboard for the right color. We set that, and set here means set to 1, and to the right piece. And here is the piece type. We had the bitboard program before, but it was almost empty, but now it's not empty anymore. So if we take a look here, I use bits, the package bits that's under math in Go's standard libraries. I move the bitboard type into this bitboard.go, and here we have some functions, some methods. For instance, count all the bits, count all the 1, that is set to 1, and we can use the function from bits. We set a bit to 1, that is our own function that we do here, put in a bit there. We can test, that means we see if it's a bit is 1 or 0. If it's 1, we return true, otherwise we return false. We have this clear, that actually means set to 0. We set the bit on certain position to 0. And this one is important, if I can find it here. That is first one. So we use a function within the bits package. Trailing zeros. It's counting trailing zeros. If it's 64, we didn't find any ones. There's only zeros. So we return 64. Otherwise, that bit position to the first bit that is set to 1 in our bitboard. And we make this function so it updates the bitboard. So if we find one bit, it turns off that bit. So we can loop through this first one and take out every bit that we find. And we also return that bit position. I also made some unit tests. They worked out well, and I will not talk so much about these unit tests. Maybe you remember I said I will take care of this parts 0 and parts 1 when we parse the fence string, and I made it complicated. So now I put that fence string directly into parts 0. So that's all. I also had to take out some of the tests of the UCI commands because they don't necessarily send something back to the GUI. You know, when we have this function is not implemented. When we made them working, I mean when we have this handle position working, I take out that test and make special test for that, like here, test handle position. And I did that for some other test new game and so on. What to-dos do we have now? For instance, we need to make moves. When we parse moves, I would like to have two commands that are not UCI, but we can use them when we run the program standalone. Print board and print bitboards. And we can start to look at the go command and see what we can do with that, because that is our think command. So let's start to be interesting now. That's all for now, folks, and to the next time, have a good one.